Welcome to the First Mold Insights, where we talk about injection molding, rapid tooling, product development, and real world manufacturing insights. Today's topic is plastic shrinkage in injection molding. Alex, we hear a lot about shrinkage in manufacturing, but for those new to it, what exactly are we talking about when we say plastic shrinkage? What's happening on a fundamental level?
Well, Mia, it's pretty fundamental, right? When we talk about plastic shrinkage, we're really looking at the percentage decrease in dimensions from when a part is hot and fresh out of the mold to when it's fully cooled down to room temperature. It's not just the thermal expansion and contraction you'd expect, though that's a big part of it. It's also tied into a bunch of other molding factors, which is why we often call it molding shrinkage. It's essentially the difference between the original size inside the mold cavity and that final cooled size divided by the original size, all multiplied by 100% to get a percentage. That difference is critical.
Right, so it's not just the material cooling down, but the whole molding process influencing it. That makes sense. And I imagine this isn't just a minor aesthetic issue. How does shrinkage actually impact the final part, its performance, its appearance, and even production costs?
Oh, it's huge, Mia. It hits you in three main areas. First, dimensional accuracy. If your shrinkage rates aren't properly controlled, your part dimensions will inevitably deviate from design specifications. We see this all the time. In the automotive industry, for example, if a door panel or a window component shrinks too much or unevenly, doors might not close smoothly or windows could bind. That directly affects vehicle performance and, frankly, safety. Second, appearance quality. Plastic parts are often expected to have smooth, pristine surfaces. Shrinkage can cause surface irregularities, warpage, sink marks, or even subtle texture changes which just diminishes the product's aesthetics and overall feel. This not only impacts consumer purchasing decisions, but can also really tarnish a company's brand image. And third, it definitely increases production costs. To keep shrinkage in line, injection molding companies like First Mold often have to take various measures, like adjusting mold designs, optimizing injection molding processes, or even needing to run different cycles. That means more time, more material, more labor. And if parts are out of spec, you're looking at secondary processing, additional repairs, or even scrapping parts entirely. All that adds up significantly to both production and time costs.
So it's not just a design headache, it's a real financial and functional problem if not accounted for early on. I can see why the folks on the shop floor need to know this, but why is it so crucial for product designers who aren't directly running the machines to grasp these shrinkage principles?
Well, they're the ones drawing the lines, right? Even if they're not directly manufacturing the part, their design choices echo all the way through production. If a product designer truly understands shrinkage, they can anticipate those size changes during production. They can optimize designs upfront for precise, consistent results. That means fewer costly surprises later on. And it's also about informed material selection. Different plastics exhibit varying shrinkage levels during molding. Knowledge of shrinkage aids designers in picking suitable materials based on specific design requirements and tolerances. Ultimately, by anticipating and addressing shrinkage issues early, it shortens development cycles, expediting product launches. It minimizes shrinkage-related problems like waste, rework, and delays, making the whole production process more cost-efficient. Designers aware of shrinkage can create economically viable products from the get-go.
That makes a lot of sense. Anticipating problems on paper is always cheaper than fixing them on the production line, especially with complex parts. So, what are some of the key factors that actually influence how much a plastic part shrinks? I imagine it's not a one-size-fits-all number.
You're absolutely right, it's not. It's a complex interplay of many variables. For product designers, a really common one to note is wall thickness. Thicker walls lead to longer cooling times, and generally, that results in greater shrinkage. Also, features like reinforcements, ribs, or engravings, they can actually resist shrinkage in those specific areas, meaning you'll see smaller shrinkage rates where those features are. That can lead to uneven shrinkage and internal stresses, which can cause warpage.
So a part isn't shrinking uniformly, even within itself. That's a crucial detail that could cause a lot of headaches.
Exactly. And for us on the mold side, we're looking at even more variables. Things like the molding process itself. Consistent molding temperature helps reduce shrinkage. Increased injection pressure, that typically decreases shrinkage. A higher melt temperature, somewhat counterintuitively perhaps, also reduces shrinkage. But then, a higher mold temperature actually increases it. It's a constant balancing act. If you maintain pressure for a longer duration, you generally reduce shrinkage, and a longer cooling time within the mold also tends to decrease shrinkage. High injection speeds? Those can slightly increase shrinkage. And one thing people often forget is that the initial shrinkage is quite large, but then it stabilizes after approximately 2 days. It's not an instant final dimension.
Wow, that's a lot of levers to pull just in the process itself. What about the plastic's own structure or the mold's design?
Yeah, the plastic structure matters a lot. We already mentioned thick walls. Parts with inserts like metal pins or bushings, they'll often have lower shrinkage rates because the insert resists the plastic's contraction. Complex shapes also tend to have smaller overall shrinkage rates compared to simple, bulky shapes. And here's a big one. Shrinkage is typically smaller in the flow direction of the plastic. So if you have an elongated part, it'll shrink less along its length than it will across its thickness. That's really important for predicting warpage and ensuring dimensional stability. Then, the mold structure itself. A larger gate size? That generally reduces shrinkage. Parts farther from the gate often have smaller shrinkage rates, and any restricted areas of the mold will tend to exhibit less shrinkage. Finally, the plastic's inherent properties are huge. Crystalline plastics, like nylons or polypropylene, typically exhibit greater shrinkage than amorphous plastics like ABS or PC. Materials with good flowability tend to have smaller molding shrinkage. And this is a major tool we leverage. Adding fillers to plastics, especially glass fibers or minerals, significantly reduces shrinkage.
Oh, that's interesting. So, a material like glass-filled nylon would shrink less than pure nylon?
Absolutely. We see that constantly on the shop floor. In fact, different batches of the same plastic can even have varying shrinkage rates, which is why consistency and material sourcing is so important.
That leads right into my next question. Given all these variables, how do you even get a handle on specific shrinkage values? Like, if I'm designing a part in ABS, what kind of shrinkage should I expect?
It's why those detailed tables we compile are so valuable, Mia. You might find a general range for ABS online, something like 0.4% to 0.7%, but when you look at the specifics, you really see the nuances. For instance, general injection grade ABS is indeed in that 0.4% to 0.7% range. However, if you opt for, say, a 30% glass fiber reinforced ABS, that shrinkage drops dramatically, often down to just 0.1% to 0.3%. That's a huge difference for achieving tight tolerances.
That's a massive impact from just adding a filler.
It really is, and we see similar effects across the board. Take PA6 or nylon 6, A general injection grade PA6 can shrink anywhere from 1.4% to 1.8%, but if you reinforce it with 40% glass fiber, that shrinkage plummets to a much tighter 0.1% to 0.3%. Even a 15% glass fiber reinforced PA6 gets it down to 0.5% to 0.8%. It just shows how powerful those fillers are in stabilizing dimensions. Or consider polypropylene PP. A general toughened PP might have a shrinkage rate of 1.5 to 2.0%. But if you use a 40% talc-filled PP, that's more like 0.0% to 1.0%. The talc acts as a filler, stiffening the material and reducing its thermal contraction. And then you have materials like PC or polycarbonate. These are typically lower shrinkage to begin with. A 20% glass fiber reinforced PC, for example, is in the 0.3% to 0.5% range. Even a 30% glass fiber reinforced halogen-free flame retardant PC can go as low as 0.1%. It's about knowing those specific grades and their documented behavior.
So it's not just about picking PA6 or PP, it's about the specific grade and fillers that profoundly change the shrinkage behavior. That's a critical takeaway for material selection, and something a designer needs to look up in detailed material data, not just a general range. Given all these factors and the wide ranges, what steps can be taken to prevent these fluctuations in shrinkage and achieve more consistent parts?
Good question, Mia. It really boils down to a few key measures we implement. First, achieving flow and gate balance. Shrinkage varies with resin pressure changes, right? So whether you're working with a single cavity mold that has multiple gates or a multi-cavity mold, you have to balance those gates. That ensures uniform resin flow into all areas. And actually what we found is it's often preferable to achieve runner balance before gate balancing, as the flow resistance in the runner directly impacts everything downstream. Second, mold cavity arrangement. Think about it. The molten resin carries heat into the mold. Under typical cavity arrangements, the mold temperature distribution forms concentric circles centered around the gate. So when you're selecting the arrangement of cavities in a multi-cavity mold,